Hello everyone, welcome to the 4.5C notes. These notes are on related rates, but specifically with volume and surface area. And so these notes are going to be similar to the ones that we've done previous to this. It's like kind of the same concept, it's just, again, new context. And so you're welcome to try some of these problems by yourself. Some of them are easier than others, but if you need any of the problems to be worked through with you, here we go. So example 1 says sand is being piled into a right circular cone at a rate of 8 cubic feet per minute. The radius of the cone is equal to the height. How fast is the height of the cone changing with the height when the height is 5 feet? So I'm going to start by drawing a picture. It says we have a right circular cone. So I guess the sand is being piled, and as it's being piled, it's making a cone. So that's kind of what I'm picturing. It's piled, it's making a cone, the cone's getting bigger and bigger. So kind of what I'm picturing. I'm just going to go ahead and just draw a cone though to help myself. So this is our cone. And sand is being piled into this cone. And so sand is a mass, and so if the sand is becoming piled into this, what's changing is that the volume of this cone is going to get larger and larger. So at the very beginning, right, of sand being piled, it might look like this. Then it's getting bigger as we're adding more sand to the pile. And so what's changing is dV dt. So dV dt equals 8 cubic feet per minute. Another way to know that that measurement was going with volume specifically was because it said cubic. So cubic is always with volume, squared is always with some kind of area. So the radius of the cone is equal to the height. So we know that this cone is essentially proportional. So the radius is equal to the height. So obviously the cone that I drew is not drawn to drawn to scale, but we know that the radius of this cone is equal to the height. How fast is the height of the cone changing? So we're looking to find dH dt when the height is 5. Cool. So we want to find dH dt, we have dV dt. So we're going to use, because of dV dt, we're going to use the volume formula. Pi r squared h over 3. So this is the volume formula of a cone. It's pi r squared times h divided by 3. And we're going to see how can we use this information. So the height is changing, so we can't plug in 5. But what thing we could plug in is r equals h, this information right here. And at the end of the day, we're concerned with dH dt. So h has to stay in this formula. But to make this problem easier on me, what I can do is replace r with h, because they're the same thing. And then this would further simplify to pi, there's 3 h's now, pi h cubed all over 3. And now I have the volume formula, but just with respect to h. And now I'm going to take the derivative of both sides because I need the formula with the rates. So if I take the derivative of both sides, over here I get dV dt. This will be pi, because that's the constant, times 3h squared, and then with respect, because we're taking it with respect to t, it'll be dH dt, and then all over that 3. But then these 3's just kind of cancel each other out. Then I'll have dV dt. So we know what dV dt is, so I'm going to go ahead and plug things in. So I know that dV dt is 8. I know that the instant we're talking about, h equals 5. And then what I don't know is dH dt. Oops, that's written wrong. And at this point, I can just solve. 5 squared is 25, so I'm going to divide by that. Both sides, I'm going to write it as 25 pi though. And I'll get 8 over 25 pi. And then this is going to be feet per minute. And that is the change in the height with respect to time. So that is our answer. So if you need any more time with that, pause it, but we're going to keep moving. So this one says the radius of a base of a cylinder. Okay, it already says cylinder, so I'm just going to go ahead and draw that. The radius of the base of a cylinder, so radius, is decreasing at a rate of 9 millimeters per hour, and the height of the cylinder, so our height, is increasing at a rate of 2 meters per hour. At a certain instance, the base radius is 8 millimeters and the height is 3 centimeters. What is the rate of change of the surface area? So at that instance. So basically, I'm just trying to visualize this. This radius is going to get smaller, so this circle is going to start getting smaller and smaller. but then this height's going to get bigger, so it's going to become more like that. So that's just me picturing it in my head, but let's see what I know. So the radius of the base, dr dt, is decreasing. So that'll be negative 9 millimeters per hour. The height is increasing, so dh dt is 2 millimeters per hour. At this instant that we're concerned about, the radius is 8 millimeters and the height is 3 millimeters. And then it says, what is the rate of change of the surface area? So dA dt, and we're concerned about the instant when the radius is 8 and the height is 3. So we're trying to find dA dt, and we need the surface area formula of the cylinder, which is, okay, this is gonna be kind of messy, so just be prepared for this. But the area of the surface area of a cylinder is this formula right here. So why this is a little tricky is because the radius and the height are both going to be changing. So they're both constant, which means I have to take the derivative of both sides before I can plug anything in. But what's tricky about that is if you guys look right here, I have two variables multiplying each other, and they both represent functions, right? This represents the radius function, this one represents the height function. And so because this is multiplication between them, I'm going to have to use the product rule. So we'll get there in a second, but I'm just getting you guys prepared for that. So I'm going to take the derivative of both sides with respect to t. So on the left, I'll get dA dt. Okay, now I gotta take the derivative of the two terms. So term one is 2 pi r h. So I'm gonna view this as like the first function, and then I'm gonna view this as the second function. So the derivative of that first function is gonna be 2 pi, the derivative of r is 1, and then we have to do times dr dt, and then times the original second function, plus 2 pi r, so original first function times the derivative of h with respect to t, which will be d h dt. So that part was messy, but then the second term over here is it's like fine. There's no, like, there's not two variables. Pi is not a variable, it's a constant. So this will be 2 pi times that 2 that drops down times r dr dt. So it's just pretty messy, but that's it. I'm just gonna check my work real quick and make sure I did not make any mistakes. Nope, everything looks good. Okay. Cool. So now I have all the information, so I'm just going to plug things in. So I'm trying to find dA dt. This will be 2 pi dr dt was negative 9, h was 3. Then I'll have plus 2 pi, radius is 8, dH dt is 2, plus, I'm going to go ahead and combine these twos real quick. So that'll be 4 pi, and then the radius is 8, and then dr dt is negative 9. And then we just have to clean that up. I'm going to keep the pi in and then combine like terms. So this first term becomes negative 54 pi. Second term, 2 times 8 times 2 is 32, so that'll be 32 pi. And then that's the last term, 4 times 8 is 32. 32 times negative 9. I'm not doing this in my head. I already had it written out, so don't think I'm super good at this, but minus 288 pi. And then those are all like terms because they all have that pi in them, so the answer is going to be negative 310 pi, and it's an area, so it'll be millimeters squared per hour. So that is the answer. Let me know if you have any questions. We're going to keep moving on. So this video is not too long, but if you need more time, just pause it. Okay, surface area of a cube. Okay, so I'm going to go ahead and draw a cube. Surface area of a cube is increasing, so it's going to get bigger. So the surface area is increasing at a rate of 15 square meters per hour. At a certain instant, the surface area is 24 square meters. What is the rate of change of the volume? So I don't know if you guys maybe think about why is this one weird? It like looks fine right off the bat. If you really think about it, it's kind of strange. And that's, it includes surface area and volume. So we're going to get to that in a second, but let's just write out what we know. So the surface area change, it's increasing by a rate of 15 meters squared per hour. At a certain instance, the surface area is 24 meters squared. What is the rate of change at that instance of the volume? Okay, well, the volume, like, we want to figure out, so our end goal is to find the volume, right? But surface area and volume, like those aren't the same formula. So real quick, the surface area of a cube specifically, that formula is going to be the area equals 6s squared. But then the area of the volume is s cubed. So they're not like combined at all, but maybe something that you notice in both of the formulas is the s. And so let's go over here real quick. If we were to take the derivative on both sides, because we're going to need this velocity formula over here to figure out the rate of change of velocity. So let's go ahead and take the derivative of both sides of this formula. So that equals dv dt, and then we'll get 3s squared times ds dt. And if I go over to the information I know, I don't have that information. I don't have s, which I guess we could figure out s really quickly because we know that the surface area, we know that the surface area is 24. So we can go ahead and find that real quick. We would just do 24 equals 6s squared. That would give us 4 equals s squared. So that means s is 2. So I guess we know what s is, but we do not know, we were not given the information for the change in the side length over time. So think about maybe what we could do. Maybe pause it. I'm going to go on though. What we need to do is what we have information about the rate of change is we do have information about the rate of change of the surface area. And in taking the derivative of this formula right here, ds dt is going to pop up. And then we could solve for ds dt using this formula, and then we can plug it in right here. So that is what we're going to do. Becomes dA dt. This becomes 12s times ds dt. This will be 15. 12 times 2 ds dt. And so this becomes 15 over 24 ds dt, which would simplify to 5/8. So that's what ds dt is. So now that I know that, I can go plug that into this other formula. Would be 3 times s squared, or 2 squared is 4, so I'm going to go put that there, and then 5/8. This is going to give me, we're just going to simplify now, 15/2, and that is volume, so it'll be millimeters cubed per second, and that is our answer. So again, stop it, pause it, let me know if you have any questions. Just like write them down on the side and we can talk about them the next day. We got 2 more, I believe. 2 more. Okay, so this next one's not too bad actually. A spherical balloon is being inflated with gas. So imagine a spherical balloon, it's 3D, it's being inflated with gas at a rate of 20 feet cubed per minute. So cubed, spherical balloon is inflating, that is our volume. So our volume is 20 feet cubed per minute. How fast is the radius of the balloon increasing? So we want to find dr dt. And this is actually 2 separate questions. We want to know how fast the radius is increasing at 1, and that's part A, and then also in B. So this piece of information over here on the side is going to work for both of them, but we're going to kind of do this in 2 separate problems. Because in this one, we're concerned about the radius being 1. So we are going to need the volume of a sphere formula, which is V equals 4/3 pi r cubed. And to do this process, we only have to really take the derivative twice. So if I take the derivative of both sides of that, I'll get dv dt equals 4/3 pi times 3r squared times dr dt. And so I'm just going to put this kind of move this all over here. Okay, I'm just going to clean that up real quick. But we do know that dv dt is going to be 20 for both situations. So I'm going to plug that in. These r's cancel out. So I'll get 4 pi, sorry, not r's, those 3's cancel out. 4 pi r squared times dr dt. And then I'm going to do a now. So a, I guess I'll do that over here to put it under a. For a, I just need to plug in 1 for r. And then I just have to solve for dr dt, so it'll actually end up being 5 over pi. I did that in my head, but see if you can figure out why. And then we were concerned about the radius, so it'll just be feet per minute. And that equals dr dt. So that's the answer for A. And the answer for B, I'll put here. Same idea, but now we're plugging in 2 because we're concerned about the instant 2. 20 equals 4 times, that will end up being 4, so we'll have 16 pi. This will be 20 equals 16 pi, which is dr dt, and I'll simplify that fraction, which will be 5 over 4 pi feet per minute. And that is the answer to B. Okay, one more problem. Water is being poured into a cubical tank. So let me draw my tank real quick. So it's a cubical tank, which means all the sides are equal. So I'm going to try my best to draw that. Okay. That's kind of ugly, but let's just pretend it looks good. Okay, so this is my cube, and water is being poured into this cube. So I'm imagining water being poured and then just kind of like accumulating here at the bottom. Beautiful picture. Okay, water's coming in, it's being poured into this tank. Each side of the cube is 5 inches. So each side is cube 5, 5. I guess this whole thing would be 5. How fast is the depth of the water changing? So we know that water is being poured into the cubic tank at a rate of 2 cubic. That's a hint. So we know that dV dt equals 20 inches per minute. And then we also know that the sides of the cube are 5. And then it wants us to find dP, or the depth. So I guess we can do, I'm going to change the word depth to an H because I don't like dt, that's just confusing. So we're going to make that, we're going to try to find dHdt. And I'm just interchanging the word height and depth because I like it better. So how fast is the depth of the water changing? So right off the bat, you might think that you should use the volume of a cube for this, which the volume of the cube would be s cubed equals v. But the tank is a cube, but the water isn't being poured in as a cube. So the base is always going to stay a 5 by 5. But like if you look, I'm going to erase my beautiful water real quick. This, like that's not a cube, right? That's because a cube, the sides would have to be the same. Like this height is not 5. And so it's also going to be moving. So the actual like area where the water is going into is actually not a cube. It's more likely, well, not more likely, it's a rectangular prism. And so instead of using the cube formula, which is the volume per cube, which is s cubed equals v, we'll just do like the normal volume formula, which is length times width times height. So that'd be the normal volume formula. However, we do know that there is a constant here. We know that the bases of this cubical tank aren't changing. So that's the length times the width. So we know that these two parts are a guarantee. And so we can actually go ahead and plug those in first. So now we have that the volume of the water is going to be 25H. And then there's my model. I have all my information. I'll take the derivative of both sides. So taking the derivative of the left, taking the derivative of the right, this will be dv dt, 25 dh dt, and then plugging in the info I know, which is 20 equals 25 dh dt. Simplifying that will be 4/5 inches per minute. And we are done with the notes. I hope you had fun. I will see you all later. If you have any questions as you're writing, just like put them in the margin and we'll make sure to get to those the next day in class. See ya.